Hello everybody, and today we are going to be going through a step-by-step process how you can derive the 3 different kinematic equations that you're going to be using in physics throughout the semester. And this is going to be a helpful process in case you forget how to get one of the equations, or if you want to verify that one of the equations is actually what you think it is. So let's go ahead and get started with a basic fundamental equation that we all learned on the first day of physics, which is F equals ma. So from this equation, F equals ma, we are actually able to pull out the acceleration. And we know the acceleration is the change in velocity over the change in time. And now we are going to pull the dt to the other side and attach it to a. So we are left with a dt is equal to dv. Now let's get rid of the dt and dv by integrating both sides. And now we are left with an expression in the end, but let's be sure that we add what we are integrating over for both of those. So for this first one, we are integrating over a time integral. So that is t initial, so the first time, and then the t final. And then for this last integral dv, we have v initial and then v final. So let's go ahead and write down our final answer after this. So we are left with a t, and that is from t final to t initial. We set that equal to v over v final and v initial. So let's go ahead and write that out to get rid of the t final and t initial. So we have t final minus t initial is equal to v final minus v initial. Now we can actually represent this as delta t. So we're going to write acceleration times delta t is equal to velocity final minus velocity initial. And then we can actually see that's one of our kinematic equations. So if I go ahead and rewrite that up here, I get the velocity final is equal to the velocity initial plus the acceleration times the change in time. And if we remember, or if you go back in the video, that is actually the first kinematic equation. So we're going to go ahead and use this equation in solving for the other 2 equations now. So now let's go ahead and take a look at how we can get that second kinematic equation of motion. So here I've written the equation from before, where we have the velocity final is equal to the initial velocity plus the product of acceleration and the time elapsed. So over here on the right side, I wrote out what velocity final equals. It equals the change in position over the change in time, because in essence, that's what velocity is. So I pulled the time over to this side, and I was able to get the velocity final times dt is equal to dx. And we are going to see this become useful as we integrate this expression on the left. So let's go ahead and take the integral of all of these terms with respect to t. And we are going to be integrating from the initial time to the final time. So here is the expression written out. And look on the right side here, we can see the velocity final times dt is actually equal to dx. So we can write dx over here instead. And instead of going from t initial to t final, we are now integrating with respect to a new variable x, which is the position. So we go from x initial to x final. You can see where this is going. That is going to equal delta x. Looking at this term here now, we have the velocity initial times time, because we are adding the time variable to the velocity initial, which is just a number in this case. And now we are going to add the second term here. But notice this one already has a t in it. And when you integrate a variable with respect to that variable, it is equal to t squared over 2 in this case. So we have an acceleration tied to that as well. So we're going to rewrite that as 1/2 a times delta t squared. And notice that this looks very familiar, and this is indeed our second equation here. So we did get this right. So we are left with the displacement is equal to the initial velocity times time plus 1/2 times a times delta t squared. Also with this equation, be careful the question does not have an initial position, because if there is an initial position, such as in a graph problem, you need to make sure that you add that to the question. And now, in order to get the last equation, which is the timeless equation, or the only kinematic equation that does not have time, we are going to again use that equation of the velocity final is equal to the initial velocity plus acceleration times time. So from this, we are going to write out the 2 different components, acceleration is equal to the change in velocity over the change in time. And then we are also going to write out the velocity is equal to the change in position over the change in time. Now notice that both of these have a similar term, that being the change in time in the denominator for both of these. So we are going to solve for dt for both of them and set it equal to each other and then go from there. So we get acceleration times dt is equal to dv. And then we are left with dt is equal to dv over a. And then similarly for the right side here, we get dt is equal to dx over v. So because we know dt is equivalent for both of those, and those are both set equal to dt, we can set them equal to each other. So we get dv over a is equal to dx over v. And now if we cross multiply, we get v dv is equal to a dx. Now let's take the integral of both sides in order to get rid of the dx and dv. On the left side, we are integrating with respect to a variable v, so we have v initial and v final. And on the right side, we are integrating with respect to x, so we have x initial and x final. Let's go ahead and rewrite this expression to the right here. So if we are integrating with respect to v and our variable is v, we are left with v squared over 2, and v initial, v final is what we are integrating over as a reminder. And now on the right side here, we don't have an x, so it's going to be a times x with respect to initial and final positions. So now that we have this, we are able to just simplify this and get the timeless expression. So let's go ahead and pull out the 1/2 in front of this. So we get 1/2 velocity final squared minus velocity initial squared is equal to the acceleration. And for simplifying purposes, we are just going to write this as delta x. To solve for the velocity final squared, we are going to multiply the 1/2 over to the other side. So we are left with velocity final squared minus velocity initial squared is equal to 2a delta x. And let's go ahead and simplify that final answer and write it up top here. We get velocity final squared is equal to the velocity initial squared plus 2 times the acceleration times delta x. And if we go back to the start of the video, that is the third kinematic equation. So in theory, you are able to derive all three of these different equations if you ever forget them. However, it is easier just to memorize them on their own, but to know that it's possible to derive these equations gives you the peace of mind that on a physics test or exam, you are going to be able to figure out, knowing what acceleration is, the change in velocity over the change in time, you are able to get all three of our kinematic equations. And again, all you need to know is that acceleration is equal to the change in velocity over the change in time. Because from there, you are able to bring the time over, get acceleration times dt is equal to dv. Whenever you see the dt and dv, make sure you take your integral with respect to that variable after the d, because that is what you are taking the integral with respect to. And that is from the initial time to the final time. Same thing for velocity in this case, and that is how we got our velocity final is equal to our velocity initial plus the acceleration times time. Hopefully you were able to find this video useful. If you did find it useful, go on over to my channel and check out any of the other videos where there are chemistry walkthroughs. And I am hoping to upload more physics kinematics video in the future. So if you have any suggestions for future videos, leave them down in the comments and I will hopefully get to those videos here in the future. So thank you again for supporting the channel.